First step of data pre-processing is check the missing value. It firstly count the number of missing value in each column. It uses X is now sum to calculate the total number of missing value for each features columns and prints the result. It identifies columns with missing values. An empty list column with not a number is created to store names of columns that have uh, missing values, and the code loops through all columns in X. If a column has more than zero missing values, its name is added to the column with not a number list, and we print the columns that contain missing values. And the second step is to check duplicates. We identify duplicate rows using X duplicated return subline series, where true indicates that a row is a duplicate of a previous row, and the sum then counts the number of true values, which gives the total number of duplicated rows. And we store the count of duplicates. The result is stored in the variable duplicate count. And for the uh, concatenate, this code combines the feature matrix X and the target variable Y into a single data frame. It concatenates X and Y column wise, and this results in a new data frame DF, where X columns remains the same and Y is added as an additional column. And for this part, let's see the AutoVis. This code uses AutoVis to automatically generate exploratory data analysis for the dataset DF, and creating charts like scatter plots and correlation heat maps and routing charts to help identify patterns, trends, and outliers. And here we can see the descriptive statistics. This code calculates and displays descriptive statistics for the dataset using describe. We could see the count, mean, standard deviation, and the minimum and maximum values. And this part, we calculate the skewness of each columns, of the numerical columns. And it's measures the asymmetry of this data distribution. Uh, and the last next part is about check outliers. This code identifies and removes outliers from the target variable using the two-key rule. We define two-key rule function and apply the function to find out outliers in rings. We remove outliers from feature and target. Drop rows corresponding to detected outliers detects extreme values that may affect model performance. And in this box plot, we could see that there is no longer any outliers in the Y. And for the data split, this code splits dataset into training and testing sets using train test built from Excel model selection. And we have 80% for training and other 20% for testing. And this part is in order to standardize and scale features. This code scales and standardize features to bring them onto the same scale. Uh, it improves model performance by making features comparable, and it prevents bias toward larger magnitude features. Uh, this part, the code computes and visualize feature importance using a random forest regressor. We first train a random forest model, and we extract feature importance using the model feature importance, retrieves feature importance scores. and we plot the horizontal bar chart uh, showing the importance of each feature. And for this part, this code trains and evaluates multiple regression models on standardized training data. Which first defines a list of regression models, includes linear regression, lasso, ridge, or and so on. And we loop through each regression, and we calculates the uh, model performance, like compute the performance metrics like MASE, MAE, or R squared. And we also plots the predictions versus actual values. And for this part, we analyze worst case prediction. It combines predicted and actual values into results, computes percentage error for each instance. And we find the worst case prediction error. And we choose the multiple linear regression because the mean square error only has 5.1. A lower MSE indicates a better fit, though absolute values depend on the scale of the target variable. And the mean absolute error, MAE, equals 1.61. It is less sensitive to large errors than MSE, making it useful for understanding general prediction accuracy. And the R square equals 0.53 means that 50% of the variation in the target variable is explained by features. This model provides a good trade-off between accuracy and interpretability. However, further improvements needed to enhance performance. And I have three flagships. The first one is model performance and trade-offs. Uh, MSE and MAE stressed reasonable accuracy, but potential missing interactions could be limiting performance. And the second one is error analysis and reliability. In high-risk application like medical prediction, financial modeling, reliance on this model could lead to suboptimal decisions. This stress the need for additional robustness checks and other methods. And the last one is model selection and further improvements. The use of various regression models provides comparative insights, and the trade-off between interpretability and performance remains key.